This lesson, we are going to introduce this idea of a Riemann sum. And a Riemann sum is named after Bernard Riemann, who was a mathematician in the 1800s. And so they were talking about this idea of integration. It was actually introduced in the 17th century, and then it was kind of more formalized by Bernard Riemann 200 years later. And we're going to use his idea to try and estimate an area under a curve using Riemann. And so it's very formula driven. It can be very formula driven. I'm going to kind of break it up into where it's not formula driven, because at the end of the day, you're just finding areas of rectangles. And so I just need to know what the width and the height is so I can figure out the area of that one, the area of that one, the area of that one, and just add them all together. So I'm going to go back to more of a geometry idea rather than trying to figure out what's happening to the formula. Some people are great at formulas. I'm okay with formulas, so I'd rather just kind of make some sense out of what I'm doing. But here's the idea that in order for you to create these rectangles, you're going to need the widths and you're going to need these heights. And so either you're going to create what's known as a left Riemann sum, which basically means these heights are going to be figuring out what this x value is, plugging it into whatever this equation is that creates this curve, and that's going to get you your height, right? And so then this x value on this rectangle is going to be the height. We'll plug it in to find that one. We'll plug it in to find this left point, and then we go to the right. So we're going to like put all these marks on here, plug in these left values, plug in these left values to create these heights, create our rectangles. And then a right Riemann sum, exact same idea, that if you're talking about this rectangle right here, now this height is based on the right endpoint, not the left endpoint. So now this height's going to be a little bit higher, right? Depends on kind of the concavity you got going on. Concavity plays a role also as to if you have something that's concave up and you are doing a left Riemann sum, and if you make a visual on this, you'll definitely see this, that if you're concave up and you're doing a left Riemann sum and you're building this rectangle, you're going to be short. So if this curve was nothing but concave up, every one of these rectangles is going to be a little bit less than what the actual area is. We're missing these little areas, so we're going to be at an underestimate. And the opposite would be true if you were doing right Riemann sums. All these heights of these rectangles are based on the right side, and if it's concave up, you're going to have these overestimates. And so what you could do is find this value and average it, and that'll give you a much more accurate, because this one's definitely going to be under, this one's definitely going to be over, and then the real answer is somewhere in between. So if you averaged it, you might get something in between. Or a midpoint Riemann sum is something that works out pretty nice, because it gets a little tricky, because let's say this is a 2 and a 3. You need to plug in 2.5 to figure out your height, which if you're trying to do it by hand, it might complicate some things. So that's why left Riemann sums and right Riemann sums exist, because they're whole numbers typically. So this is, if you have a calculator, not a big deal, and it's going to give you probably most accurate of the three without having to do twice and then average the two of them. So that's the idea. And we have this formula, and this formula right here basically is this change in x ends up being the widths, right? So if you're going from a 0 to 8 and you want 8 individual rectangles, then the width is 1. So this would be 1 on each of these things. And then these are you plugging in a particular x value to find the heights. So that's like the first x value being plugged in to find its height, the first x value, then the second x value to find its height, on and on and on and on. So it's just giving you heights and widths, and then you multiply them together to find that area, heights and widths, multiply it together to find that area. And the widths are going to remain the same because you're turning it into widths that are all equivalent. So let's go through a problem. And this could be a very formula-driven thing, but I'm going to go ahead and make a visual on it, see if I can make some sense out of this. So it says, find the approximate area under this curve. So we have a quadratic from 0 to 8 using a left and right Riemann sums with 4 subintervals. So since there's only 4, that's fantastic. I'm going to avoid a formula on it. And I'm just going to find the areas of 4 rectangles and add them together. We're going to draw a picture to help this. So eventually this look, when we eventually do the calc behind it, is going to look like this. We're going to find, we're going to do the integral from 0 to 8 of this quadratic, and this is going to always find us the area under the curve. So that's the eventual look of what we're going to be seeing. But for right now, we're going to we don't have the calc to do it. So we're just going to go ahead and do kind of the by hand version of this. So what I need is a visual, and I am doing 4 subintervals from 0 to 8. So 2, 4, 6, 8. All right, so there's that. And then, excuse me, I need heights on this. So I'm just going to plug in some values. We're going to get a 4, 16, 36, 64. So I'm not going to try to be perfect on this, but one thing I do want to know is that I'm doing a left Riemann sum on this one. Right, and so I'm going to not be perfect on this. So when I plug in 0, I get 0. When I plug in 2, I get 4. When I plug in 4, I get 16. When I plug in this, I get 36. So this is not to scale, but it gives me some values that I can work with. We'll have a 64. So when I plot these points, I have some sort of a quadratic-ish look to it. At least it's supposed to. All right, so there's my quadratic. And what I'm going to do is I'm going to create rectangles. These rectangles are, here's the width, and this is going to be the height for my rectangle. So my first rectangle has 0 height, right? And then when I do this rectangle, I'm going to base it on this left endpoint. So there's that rectangle. When I do this rectangle, here's the height of the point on the left. And there's that rectangle. And then when I do this one, here's my coordinate. So my height is going to be this. So those areas are, my area is 0, because each of these widths are 2. So I have an area 2 times 0, I have an area 2 times 4. So I have a 0 plus 8. And then this is a 2 times 16, so I'm getting a 32. I have a 2 times 36, which is 72. So I'm going to add those areas together. So 0 plus 8 plus 32 plus 72. That area is about, well, that area is 112, and that's a rough idea of the area under the curve. However, I'm missing pieces. So because of that concave up, and I'm doing left Riemann sums, this is definitely an underestimate. All right, so let's say we go to the other side. We do our right Riemanns. So I'm using the same graph. I have 2, 4, 6, 8. Each of those widths of the rectangles are 2. And then I just got to figure out all the heights to it. So 4, 16, 36, 64. So if I plug in 2, I get a 4. I plug in a 4, I get a 16. I plug in 6, I get 36. Plug in 8, I get 64. So again, it's supposed to be some quadratic-ish looking thing. And then this time when I do my width, so here's my width, my height on this one is based on the right endpoint, which means my rectangle here looks like that. This one looks like this. This one looks like this. And then this one looks like this. All right, so definitely I'm going to give an overestimate on this one, but this is going to be a 2 by 4, so that area is going to be 8. This is a 2 by 16, so that area is 32. This is a 2 by 36, so we're looking at 72, and this is a 2 by 64, 128. So that's going to give a very different area. So this time our area is going to be 8 plus 32 plus 72 plus 128. If you add all that together, our area is 240. Now that's a very big difference between those two. We have an area of 112 for a left Riemann sum. We have an area of 240 on a right Riemann sum. If you were to average those two, that would probably be a far more accurate because it would take away some of the missing area and it would average it with some of the extra area. So, but this is definitely an overestimate. And it definitely has to do with your concavity is we were concave up, making a right Riemann sum. So we were definitely going to have extra value on this. So there's a concavity piece that you can also dig into to try to figure out without having a visual, whether you have underestimates or overestimates. But I just like to draw the picture, and then I can just kind of really old school this and not be so dictated on a formula that I don't know if I'm okay with all the time. It gets a little confusing sometimes. So try the picture. I think the picture helps out very nicely, makes things very, very straightforward.